All right, so we are beginning chapter 3 today. And for the pacing of our summer school class, the beginning of chapter 3 will be on the first unit exam, but only through 3.2. Okay, so today we're going to be covering 3.1 as well as 3.2. And for 3.1, it's called defining the derivative. And so anyone who's ever had any experience with calculus before, this word of derivative should sound very, very familiar. And we're going to spend basically the next few weeks thinking about what a derivative is and just about a bazillion ways to find a derivative. Okay, so the idea of what is a limit and how do we find limits, this first bullet point right here. So what is a limit and how do we find limits? All of that decision making that you're practicing, we're going to continue to have to make similar decisions throughout the course where we're saying now it's what is a derivative and how do we find different derivatives, okay? And so I really want us to be thoughtful about as we start to learn different strategies later on this week and next week. We're going to learn so many, it's going to be so important for us to be thinking always, how do I know that I should use this strategy, okay? And so we've talked about what a limit is and how we find them. We've talked about a lot of different strategies. We've also talked about this word continuity and how do we know if something is continuous versus discontinuous. And so I know that was sort of a small piece in the lesson, but it is actually a really important concept because if you'll notice, a lot of the times when we're looking for limits, we're actually looking for continuous or discontinuous parts, okay? But one thing that I want to sort of start to bring back in our brains is the idea of slope, okay? And so I'm wondering if we can do a very quick brain dump here. Tell me all the things that you know about slope, okay? When you hear the word slope, what is it that you think? Let's throw some things in the chat and let's see what we get. All right, so we've got slope is rise. Oh, the morning handwriting, rise over run. Rate of change, I love it. Rate of change. Y equals mx plus b. I love it. And I saw a tangent line in there. So y equals mx plus b. All right. And let's see, tangent line. All right. Before we move on, this is a really good brain dump. Can someone tell me another way of saying rise over run?
Isn't it y1 minus y2?
Yeah, y1 minus y2. And then, yep, over x1 minus x2. Good, good, good. And so I just wanted to make sure that we are really careful about this one because, yeah, Diego, I was like, I don't want to call you out because this is actually like the #1 common mistake, right? Is that we're so used to saying rise over run that we sometimes forget, like, rise means the y values and run means the x values, right? And that's going to be really important because we are going to be finding a lot of slope and I don't want us to sort of mix up the order in which we plug in our x's and y's, okay? So great job with that little brain dump, thinking about what we know. And Alberto, I love that contribution as well. Let's just squeeze that one in right at the bottom here. That alternatively, we can say y minus y1 equals m parentheses x minus x1, okay? Now, just as a sort of heads up, even though we love y equals mx plus b, if I could go back and tell all of the middle school and early high school teachers one thing, I would say, teach y minus y1 equals mx minus x1 more than y equals mx plus b. We're going to be using this one a lot more, which is why I'm highlighting that right there. But I also want us to remember that our slope is going to be the y2 minus y1 over x2 minus x1. Okay. Great, great, great. So what's new? All right, we're going to spend today thinking about average rate of change and instantaneous rate of change. I am, for better or for worse, notoriously lazy about writing out whole words. Okay. I think I don't know why it is. I think it's because I'm like scared if I take the time to write out all 4 words for average rate of change that I might not get through the lesson or whatever it is. But, or maybe it's just for comfort or for ease. But for average rate of change, I tend to write this as AROC, as in average rate of change. Okay. Again, this is I'm just going to say it's a laziness thing. Okay. And then similarly for instantaneous rate of change, I tend to write that one as IROC. So instantaneous rate of change. Okay. So if you see AROC and IROC, you'll see average rate of change and instantaneous rate of change, all right, in your brains. Actually, I do know where that came from. I feel like a long time ago I was teaching and some students were like, can we just not write out the whole thing? And so we just started writing it as AROC and IROC. So there you go. All right, so here's a quick launch to think about, all right? So the graph below shows the position functions of 2 runners, runner A and runner B, who run a 100-meter race and finish in a tie. Anyone in here either run track in like high school or just like to run for funsies? All right. Nice, nice for exercise. Hey. All right, well, anyway, we have 2 runners here. Okay, and so we have runner A and we have runner B. And for the sake of this, let's just go ahead and I'm going to color runner A in the pink. And let's do runner B in a different color. Judy, find a different color. I feel like there are so many wonderful colors on Notability that, as silly as it is, sometimes I can't decide what color I want to use. And then you can like make your own, which I haven't done yet, but I know that you could do that. Okay. Anyway, we have runner A in the pink, runner B in the green. I hope no one is red-green colorblind. If you are, I'm really sorry, but I'll do better in the future. So we've got runner A and runner B. So I'm wondering if we can take a look at question A, which says, compare how the runners run the race. Okay, so in other words, runner A and runner B, they finish at the same time, but tell me about their race. Like, tell me how they're running. Okay, and I'll give you a moment to kind of think about that. You can either unmute yourself or you can throw it in the chat. I'll leave that up to you. It's okay if you still have sleepy voice and you would prefer to chat instead of speaking out loud.
So if I could speak, runner A had a constant rate throughout his race, and then runner B started off slow and picked up the pace halfway through.
Excellent. All right, runner A is constant rate, runner B starts slow and picks up the pace. All right, thank you, Diego. All right, so runner A runs the shortest distance between the 2 points. A is constant with not. Okay.
Oh no, I have my earpods, but whenever I connect to my computer on.
All right, so I do want to actually address that idea. So it's not actually the distance. Yeah, this is talking about the meters that they run per second. So this is a distance graph, but we're looking at more the sort of slope of the line. What does that tell us? Okay. So it's not like a map necessarily. Yeah. Okay. So that constant rate, maybe another way we could say that is that runner A is running at a constant speed. Okay, so maybe constant speed might be another way to frame the idea of how runner A is running. Okay. Runner B, I would agree, sort of, he or she sort of starts slowly and then starts to pick it up and then is like running actually much faster than runner A at the end, but only to get to that same finish line at the same exact time. Okay. So we can say here that runner A has a constant rate or speed, but runner B starts slow and picks up the pace. Okay. All right, let's take a look at question B. What is the average velocity or speed of runner A? What are our thoughts? How might we find that? All right, I see 100 meters over 12 seconds. All right. So average velocity. Okay, so let's write this down for a second. Average velocity equals, I'm going to write delta distance or change in distance over delta time or change in time. Okay. If we look at our distance over time, what kind of values are the distance? Are they x values or y values? These are y values. Okay, so this is very similar to delta y over delta x, or we're actually finding the slope of the pink line. Okay, so when we find this average velocity and you all are telling me 100 minus 0 and then 14 on the bottom, let's see where those numbers came from. Okay, so if I were to write the coordinate of this point down here, I might write 0, 0, as in at 0 seconds, they are 0 meters. They've not gone anywhere. But if I were to write the coordinate of this point up here, I might write 14, 100. Okay. And I'm going to actually just kind of highlight the axes here. I love the content of this particular graph, but I don't really appreciate their color coding. I think it makes it a little harder to read. Okay. But if we look at these 2 points, 14, 100, and 0, 0, if we want to find the average rate of change between these two, we can plug them in to our slope formula. Okay. And so when we do that, we end up with 100 minus 0 over 14 minus 0. And we'll end up with, let's see, 100 over 14, or we could reduce that to 50 over 7. And what are the units for this velocity? Meters per second, thank you. And Matt, I know you've been putting the units in there with it. I just wanted to make sure that we were all okay with what the actual units are for this, okay? So when we say average velocity of runner A, we just plug in our y2 minus y1 over x2 minus x1, simplify, we get 50 over 7 meters per second, okay? Now, based on that, I'm wondering if you can tell me about when the velocity of runner A is the slowest, okay? So this whole race that runner A is running, when is runner A going the slowest and when are they going the fastest? Okay, so I see one guess that maybe it's the slowest at 0, 0. Okay, maybe at the beginning and the end. Okay. These are all really good guesses. But one thing I want us to keep in mind is when we're looking at their velocity, we're really looking at sort of the rate of change. And this rate of change is always 50 over 7. Okay, and we set up here earlier that runner A has a constant speed. All right, and so since we have like an actual line, a linear function with a constant slope, what we can say is that A has a constant velocity. Okay, and therefore that is A is always running at 50 over 7 meters per second. Okay. Abby, let's hold on to that thought for one moment. Okay, I love that you brought up this idea of instant velocity, but let's hold on to that idea for just one moment. Okay. All right, so before we move on to runner B, let's just kind of look at what we have for runner A so far. We've got runner A has a line, all right? We were able to find the average velocity, and we found that average velocity to be 50 over 7. And it turns out that runner A is one of those people, like the race starts and they're just running the same speed the entire race. Okay, they're running the same speed the entire race. But as you said earlier, runner B sort of approaches the race differently. Okay, so runner B starts off slowly, starts to get faster, and then gets even faster at the end. Okay. So I'm wondering, based on that, if we can answer part D, which is what is the average velocity of runner B? That's a great question, Matt. So when we're thinking about average velocity, okay, turns out everything that you all said earlier about this idea of slope being rate of change, okay, slope being rate of change, and knowing that rate of change is y2 minus y1 over x2 minus x1, it turns out that anytime we see average rate of change, all we need to do is use the slope formula. Okay. So this word average here, that tells us delta y over delta x. Okay. And when we see this word average here, it's also going to mean delta y over delta x. Okay. And so if we kind of write this out again, we'll get average velocity, which equals delta distance over delta time, which equals delta y over delta x. All right, so that average is the thing that tells us that. Now this time though, we can't say that's the slope of the pink line necessarily. Like I think it happens to be, but we're looking at actually like the green curve, okay? And so all we need to do is find the ending point, which is 114, right? 100 is the y value, 14 is the x value. And we subtract the x and y values of the starting point. And it turns out that we'll get the same exact average velocity. Okay. Now, one of the things that that might seem weird because they have different paths, but if we think about this maybe in terms of like a grade analogy, okay, you know, as an instructor, I see students approach the class with a lot of different sort of mindsets. Some people come into class and they're like, I'm going to do all of the assignments. I'm going to do them to the level I need to and make sure that I check off all the boxes so that I get to the grade that I want to get, right? Then we have some other folks who are like, I didn't know it was the first week of class. I didn't know that we had these assignments due. Oh, I guess I should really start to study. Oh crap, I really want that grade I want, so I better really just cram towards the end and make sure I'm dedicating hours of my life to calculus, right? Some of us are going to choose that path. And then I would say that some of us in here, there's maybe like a third category where people are like, I'm going to start off super strong. And then I'm going to make sure I have a really solid foundation. And even though there's more work at the end, it turns out because I had set myself a really good foundation, I don't have to work quite as hard towards the end. Okay, so there's lots of different paths to that same grade, and everyone has a different one. All right, so some of us might be a little bit more on the steady, and some of us might have sort of variation in how hard we are working. And some of that might be due to like things outside of this class, you know, life happens, but it might impact our ability to dedicate time to our coursework, right? But at the end of the day, if you can still get to that finish line, then effectively you have sort of the same average velocity or that same average workload, okay? Now, I think for part E here, it says, when is the velocity of runner B the slowest? Maybe now we can sort of answer that question a little bit better, okay? So when on the graph would you say is runner B running the slowest? Yeah, somewhere in the beginning, right? Somewhere in the beginning, we can say that the velocity is kind of slower, okay? When would runner B be running the fastest? Right before the end, right? This is the mad dash to the finish. Like maybe I can catch you, maybe I can pass you in that last stretch. Okay. I agree that velocity is slowest at the beginning and fastest at the end. I'm wondering how we can tie that back in to this word. Okay, so how can we use the word slope to help us determine sort of how slow or fast runner B is running? The slope at that point. If we look at, I'm going to zoom into the graph a little bit more, okay? So if we zoom in on this graph a little bit more, look at the slope sort of at the beginning. That's kind of like flatter, right? But as we get close to the end, the slope is like going up pretty fast. It's pretty steep. And so when we're looking at a graph of position, and we want to talk about the velocity, we're going to say that it is the slowest at the start, and that is the least steep slope. Okay. And it's going to be fastest at the end, where it is the most steep slope. Okay. And so Abby, that kind of brings it back to what you were saying earlier, which is that's why we're looking at sort of this idea of instantaneous velocity. Okay. So at a specific moment, excuse me, at a specific moment in time, runner B is actually moving at a different speed than runner B is moving at a different moment in time. Okay. And so this should be something that like maybe you've seen in like, middle school or high school, thinking about being able to read a graph. And so that would be one really important skill for you to practice, okay? But for right now, we are gonna move on to rates of change, okay? And so we're gonna have a chance right now to practice finding actual values from a graph. We're going to spend some of this time working together, and if we have time, we'll spend some of it working in small groups. All right, so I have a great question in the chat right here. For those of you who have, if you have taken calculus before, and you're starting to think ahead, the graph, the derivative of the position function is velocity, and the derivative of the velocity function is acceleration. Okay, so I know that some of us in here had prior experience with calculus, and so it is important, I think, the second time around, or anytime that you're seeing things again, to really think about how does this connect to what I've learned before. Because I don't want it to be a case where it's like, oh, I actually didn't really learn anything new. I'm just kind of seeing the same stuff over again and it still doesn't make sense, right? So this might be one thing if you've taken calculus before, to start to think that, okay, there's something about derivatives. How are these functions related? Okay, and so one thing that we'll see probably next week is this idea that position, if I take the derivative, I end up with velocity. And if I take the derivative of that, I end up with acceleration. And so we'll spend some time working on that next week. But I love the thinking ahead. I think that's so, so important. Okay, so let's do some what we normally feel like is math. Let's draw some pictures and let's crank out some numbers, right? Use a calculator. That's what math is. Just kidding, it's not. Math is so much more than that. Okay, so we have this graph. I'm going to highlight the axes again. I don't really appreciate the way that they've done the diagram. Maybe I could do this in a different color. So here is like the x-axis, and here is the y-axis. Okay. I don't know why they made it so thin and the same color as everything else, but there we are. So we've got this graph. We don't have any units, so we don't really need to worry about that right now. But if there are units on our graph, we really want to be thoughtful about that. Okay. So part A says draw dot. What I meant by that was draw a dot. Okay. Draw a dot on the graph where the x equals 20. Okay. What is the y value of that point? So what are our thoughts? What is the y value of at that point? And I think we can sort of apply. Yeah, I think 300 is a great guess. So if we were to draw this point out, we might say that at x equals 20, we'll be right about there. And that the y value there is about 300. Okay. Now let's draw a second point in part B. Okay, so draw a dot on the graph where x equals 60. And what do we find for the y value of that point? All right, you've already got it. 700. I think that's a good guess. All right, now we have a red point and a blue point, and part C says find the slope of the line that connects the 2 points you drew in A and B. And so if we were to sketch a line that goes through those two, we might end up with something like this. Ooh, that's not bad. Nice job, Judy. Sometimes, you know, it just sort of misses the point on there. It's definitely intimidating to be drawing in front of everyone, but here we go. We've got this point. We want to find the slope. Matt has set it up for us already. I love that. So delta y over delta x. And we're going to get 700 minus 300 over 60 minus 20. All right, so we're just plugging that into our y2 minus y1 over x2 minus x1. So we've got like the blue point right here. And we've got we've got the red point right here. And when we simplify this, we'll get 400 over 40, or we will end up with a slope of 10. Okay. All right, any questions about example 1? All right, if you have a question, you're welcome to ask it, even if we move on from question 1, that's okay. Okay, so question 2, slightly different wording here, right? Because I think it's just as important to think about the process as it is to like think about the wording, all right? So this one says compute f of 40 minus f of 10 over 40 minus 10. So let's start there. Anybody have some values that I can plug in, particularly to the numerator? I think the denominator is a little bit more straightforward.
200 minus 400.
Yeah, 200 minus 400, good. So let's kind of use that color coding again, just so we are aware of where all the points are. So the first point would be like 10 and 400. So that might be like right here. And then the second point would be like 40 and 200. That point would be right there. And so what we're doing is finding the slope of the line that goes through those 2 points, okay? Now, do we anticipate that our answer is going to be positive or negative? Just looking at this picture right here. Yeah, we want our answer to be negative, right? And so when we think about the actual line, oh gosh, I don't know if I could do it again. If we think about this actual line right here, right? If we connect it either in our brains or sketching it out on the paper, we can see that that line has a negative slope, okay? And with our computations, we'll end up with negative 200 over 30. And if we simplify that a little bit, we'll end up with negative 20 over 3. Okay. And that is good because a negative answer corresponds to our picture, right? Those two make sense. If I had drawn a positive line, I should end up with a positive slope, right? All right, part B says draw your answer from part A on the graph. We've already done that. We're good to go. Okay. All right, let's take a look at example 3 here. Okay, so with example 3, we've got a few different parts to it. All right, so let's take them piece by piece. So part A says identify 2 points where the slope of the line connecting them is 0. And I think this might actually be, yep, okay. This might be a good time to try that annotation piece, all right? So before you start drawing, let's zoom out a little bit so maybe it'll be easier for you to draw. But go ahead and try drawing. Where might there be 2 points, right? Where when you connect them, the slope of that line between them is going to be 0. I see a couple of guesses in the chat. I see a couple pictures going on here as well. Very nice, very nice. Good, good. All right, so we see one variation. Now, I will say that there are actually more answers. All right, great. I see that's the one that Matt put into the chat. Perfect. Nice job, May. Yes, that is another one. Okay, I love it. I love it. So if I were to go through and just go over what you've drawn, we do in fact have one here. I love that. Okay, I could connect those 2 points. That would give me a slope of 0. I could connect these 2 points. That would give me a slope of 0. I could connect these 2 points. That would give me a slope of 0. Are there more? Or is that it?
It's infinite, right?
I think in this particular diagram, yes, we could find an infinite number of them. Okay. And Matt, I really like the way you summarize that, where it's any 2 points where the y value is the same. Okay. And so, yep, I see one more up here. Exactly. Something like up there would be absolutely fine. I could even do one here. And all of these pink lines satisfy that phrase, any 2 points where the y value is the same. Okay. And so if I go ahead and jot that down here, maybe I could write for myself that any 2 points that have the same y value will have a slope of 0 for the line connecting them. Okay, so any 2 points that have the same y value will have a slope of 0 for the line connecting them. Okay, and one thing I just want us to remind ourselves is that a horizontal line has a slope of 0. Okay, so a horizontal line has a slope of 0. Whoops. All right. Let's take a look at part B. Okay, so part B, which one is larger, the slope of the line connecting x equals 40 to x equals 60, or the slope of the line connecting x equals 40 to x equals 70? All right, so what are our thoughts? I'm going to do this one in the green. Do this one in a different color.
40 to 60, right?
Let's see. The first line should be from here to here, right? Whereas the second line is going to go from here to x equals 70. All right. If we were to sort of sketch the line that goes between these, that might be the green one. And then the purple one looks to be pretty close, but maybe it's a touch less steep. Yeah. I don't know about you, but there are oftentimes I look over the numbers that I've chosen. I'm like, why did I choose these? I could have chosen ones that were much more clear, right? Someone says the green one has a steeper slope by a tiny bit. That is accurate, okay? My goal with this was not for us to be, you know, splitting hairs here, but clearly that's what I've done. So we can say that the green line has a slightly steeper slope than the purple line. So this idea of looking at steepness is going to come up quite a bit as we move through, through this unit, okay? So we're going to look a lot at horizontal lines. And anytime we see a horizontal line, we're thinking slope of 0. We're going to look a lot at steepness, like which one is steeper than which one, or which one is less steep. Okay, so we're going to compare a lot of steepness of slopes. And let's see what else we're going to take a look at. All right, so let's take a look at these last two questions here. Is the slope at x equals 10 larger or smaller than the slope at x equals 30? Okay. Now I'm going to zoom in here so we can just kind of see this graph a little bit better. Let's pick some numbers, or colors. So maybe x equals 10 is going to be in orange, and x equals 30 is going to be green. Now, earlier, a few folks mentioned this idea of slope at a point. And one of us even said at the very beginning that we were going to be looking at tangent lines. Okay. And so, yes, that is going to be a really central theme for us here. And when we look at these, the way we draw them is going to be really important. Okay. So if I think about the slope at x equals 10, I'm really saying I'd like to know the slope at that orange point, okay? And when I say find the slope at x equals 30, I really want to find the slope at x equals 30, okay? Now, I think these two are going to be fairly close, all right? But if I were to sketch the slope here of the orange one, it might look something like this. Okay. That orange line is a good visual example of something we call a tangent line. Okay. A tangent line, meaning it's going to be a line that just touches our curve in only one place. Okay. Only one place. And it sort of follows the direction of the curve. Okay. So I've seen some folks, let me erase this and draw a example of something I've seen folks do. Sometimes students are like, I know that this is the point, and so the tangent line is going to go like this. I mean, the red line touches the curve at one point, so why isn't that a tangent line? And I'm wondering if anybody has some ideas around that. Why is that red line not a tangent line? It does cross through the point, okay? And in essence, it almost crosses through the graph. And if I were to think about the slope of this line, would you say that's positive or negative? Yeah, the red line that I drew has a positive slope, right? But this, if I look at the actual graph, what kind of slope does this graph have in this region? Is it positive or negative? It's negative, okay? And so we want to we want to add a little bit to that definition of a tangent line. It's not that it just touches the curve at one point, but it also follows the direction of the curve, okay? Meaning that if the slope of that curve is negative in that region, we want the tangent line to have a negative slope as well. Okay, so it's going to be a line that touches the curve at just one place, but it also follows the direction of the curve. Okay. So that being said, let's go ahead and find out the, draw the slope of the second point at x equals 30. If we were to draw a tangent line here, it might look something like this. Okay. Actually, I think that's not a great picture. Let me fix that a little bit. Maybe something like that. Okay. Now we are sort of splitting hairs here, but I'm wondering if you can tell me which one of those has a larger slope. Okay. So tell me why x equals 10 has a larger slope. Okay, it is steeper, has a greater incline. Okay, so this is, I think this question highlights the idea here that ties into steepness, okay? So I love the conversation we're having. It is, the orange one is more steep, but because it's a negative line, we have to tie in what Abby's saying here. It's more steep, but in a negative way, okay? So we might even say that at x equals 10, the slope is more negative than the slope at x equals 30, right? That I think would phrase what you all are saying accurately, that you're saying the slope at x equals 10 is more negative than the slope at x equals 30. That is 100% accurate. However, when we're talking about larger or smaller numbers, is -5 bigger or is -4 bigger? Yeah, so is -5 bigger or smaller? -5 is actually the smaller number. And I know that's so weird for us to think about, right? On a number line, that makes sense. But this question is not asking which one is more steep, it's actually asking which one has a larger slope. And so we need to incorporate that idea of positive and negative numbers here. Okay, so x at equals 10, the slope is more negative than the slope at x equals 30. Therefore, we can say that, therefore, the slope at x equals 10 is smaller than slope at x equals 30. Okay. I know that's weird, but I did want to use that to highlight this idea that we need to make sure we read the question carefully, that what is it asking us to compare, okay? All right, we've got one last picture to take a look at here. Which is larger, the slope at x equals 60 or the slope of the line connecting x equals 40 to x equals 80? All right, so let's do this. X equals 60. We're going to do that one in pink. And we'll do this one and maybe a light blue. All right. And practice drawing these on your own. And let's see if we have some ideas for which one is going to be larger. Now that we're clear on what it means to be larger. Okay, we've got to guess at x equals 60. So let's see, let's put this on a picture and see what we think. So at x equals, I'm going to draw the blue line first, because I think sometimes it's easier to think about 40, 60, 80. 80 is going to be all the way here. I think it's easier to think about like connecting 2 points on a line, because that's what we're used to. And so if we connect those, that would be the blue line, okay? And if we think about it, x equals 60, that would be right here. And if we were to sketch the tangent line, we wouldn't draw one that just randomly goes through the point, right? Let's see, let's count. I know I hate the layout of this graph, but we have 10, 20, 30, 40, 50, 60, 70, 80. Yeah, so I think it should be 80. All right. But when we think about drawing our tangent line, this would be wrong. It does cross or touch the curve at one place, but it doesn't follow the direction, right? It doesn't follow the direction. We want our slope to be positive here. So I'm going to erase this pink line and draw a better pink line, which sort of follows that curve a little bit better. Okay. And so I think from this picture, we can see that the pink line has a more positive slope. And since we're thinking about positives, it's not weird like part C, right? The bigger the positive number, the bigger the number. So we can say that the slope at x equals 60 is larger than the slope of the line connecting x equals 40 to x equals 80. Okay. All right. Any questions on all these graphs that we've taken a look at so far? All right. Well, let's actually take a break. All right. So we're going to take a break right now. We're going to finish up 3.1 when we come back. And then we'll go ahead and jump into 3.2. Okay. So it is just about 8 o'clock right now. So let's be back at 8:10. All right. So I'll see you folks back here in 10 minutes. All right, so before break, we took a look at a lot of different graphs. And so before we move on to the next section, I want us to think about what these rates of change look like. And in particular, I want us to have sort of images that we are sort of thinking about every time we see these phrases, okay? So as I mentioned in the beginning, we're talking about average rate of change as one concept, all right? And that I often abbreviate that as AROC. Now, what we're going to do here, I'm just going to draw sort of a general function, okay? So we're going to say for any general function, it doesn't actually matter what it looks like, but what would an average rate of change look like for that function, okay? And so if we think about this, we've got this function. Okay, let's call this f of x. And the actual shape, again, doesn't really matter so much, but somewhere along this curve, we're actually going to have two specific points, okay? And in particular, we might have one point that is, let's say here, and we'll call this A, and like it has an X value of A. And what would I call the Y value of this point? Throwing my pencil. All right, yes, F of A, exactly. So we have A, F of A, right? That's what we could call one point. And what about if we had another point somewhere else on the graph? Not there. Let's maybe say right over here, and let's call this B. Then we could call the Y value of that one F of B, okay? And if we connect the line, or we draw a straight line that connects the 2 points, right? Just like we've been doing in all of the graphs before, we would end up with a line that maybe looks something like this, okay? Now, so far, we've just called it the line that connects 2 points, right? But there is a more specific name, and it is important for us to think about that vocabulary. So in particular, this blue line that goes through the function in 2 different places, this kind of line is called a secant line. Okay, so this is called a secant line. Now, I want us to write a few things down, okay? So we're gonna write this in words, again, because I think that when we hear things, sometimes it makes sense, but when we only hear them and we don't see them and we don't write them and sort of engage in all 3 of those learning pieces, then sometimes that information is not as sticky in our brains as we want it to be, okay? So first, let's talk about finding the slope. Okay, so to find the slope of a secant line, right, we can say the following. So typically we say slope is going to be the letter M, all right? And if I were to use the purple and green points that I have listed above to fill in the slope formula, how would I write that? Yeah, there we go. If I wanted to find the slope of that, I could say f of b minus f of a over b minus a. And this is our a and f of a, and this is our b, f of b. Okay. So to find the slope of the secant line, we can just use this particular formula, okay? In other words, if someone says, find the average rate of change, just like we did in that question about the 2 runners, find the average rate of change, then all you're going to do is find your 2 points, plug them into the slope formula, okay? Any questions about the average rate of change? All right. So one way that I can ask you to find the slope of the secant line is find the average rate of change, right? So one way I can ask you to find the slope of the secant line is find the average rate of change, okay? But another way that I can ask the same thing is find the slope of the secant line. Okay, so we can sort of use both ways to ask you to find the average rate of change. Okay, can use both ways to say, find that average rate of change. And that in particular is going to be one of the more challenging pieces of this next unit, is there's actually going to be a lot of different ways for me to ask you to find slope. And so it's going to be really important for us to make sure that we've got that in our brains. Okay, if she says this, it means find slope. But if she says this, it also means find the slope. Okay. Yeah, so average rate of change. Okay, so AROC is how we find the average velocity when we are given information about the position. Okay, so I love that idea when we're saying find the average velocity and we have information about the position, then we want to use that slope formula. Okay, that's a great question. All right, let's finish this section up. Let's talk a little bit about instantaneous rate of change here. All right, so for instantaneous rate of change, we're also going to draw a picture, and we're actually going to draw two pictures to kind of help us visualize this a little bit better. Okay, so let's say that I have some function f of x. Okay, and because I know I'm going to draw a second picture, I'm going to make a copy right now so that we can take a look at both pictures that are actually the same. Okay. Now this time, however, we're looking at just a single point on the graph. And so if we think about a single point, all right, maybe we have a point right here. Okay. And if I said this point, let's call this x f of x. Okay, so we'll be a little bit more general here. Let's call this x f of x. If I ask you to find the slope at that point, then what we're really looking at here is finding the slope of the tangent line. Okay, so notice our vocabulary change here. It's not the secant line anymore. It is the tangent line. Okay, that line that sort of touches our curve in just one place, but also follows the path of that curve. Okay. Now, here's the deal though. If I ask you to find the slope of that point, we can sort of eyeball this and kind of count, but that's not necessarily very accurate. Okay. So here's what we actually do. We take the point that we want. Okay. Hopefully that's close enough. We take the point that we want. And we're going to call that the same name we called it over here, x f of x. Okay. Are you folks ready for one of the biggest concepts in calculus? Because we're going to talk about that right now. So I just want to make sure we're ready. Okay. It's a very exciting moment in your mathematical careers. Okay. All right. So I'm going to zoom in on this second graph. We're going to draw some more things on it. Okay. So I've got this graph. I have this point. I want to find the slope exactly at that point. But all I know is how do I find a slope between 2 points? right? In order to find slope, we have to do y2 minus y1 over x2 minus x1. So here's what we're going to do. We're going to be very clever mathematicians, and we're going to find a point that is really close to the point we want. Like stupidly close, okay? So very close to the point that we want. And the distance between these 2 points in the x direction, I'm just going to call that h. Okay, so I started at x and then I went over h units. How could I write the coordinate of that red point? Yeah, like even closer than those numbers. So like 0.0000000. Good, good, good. Okay, so the x value of this would now be x plus h. And the y value, yeah, there we go. The y value I want to make, I see some great inputs here. I want to be really respectful of the fact that we're all typing. And so sometimes we don't type the way that we mean to say this, but I want to find f of x plus h, like the x plus h, that's all gets put into the function. Okay. Yes, the y value for the x value of x plus h. Perfect. That's a great way of saying that. Okay. So because I only know how to find slope one way, I only know how to find slope if I have 2 points, I need to come up with this second point. But if I pick a point that is too far away, like if I pick one that's all the way over here, then really I have like a secant line situation. So what I'm saying is let's pick 2 points that are really close together. They're basically right on top of each other because the h is so small. And so we actually can have 2 points and now we can plug them into our slope equation. Okay. So let me zoom back out for a moment, right? We've got our tangent line and we said in order to use strategies that we know, we have to make up this second point that actually that is really close to the first point. Yes, okay, so that's what we're going to do right now. How do we find this point? Okay, now let's write out some words. So to find the slope of the tangent line, all right, to find the slope of the tangent line, let's use m equals y2 minus y1 over x2 minus x1. Okay. So that is slope will be, let's plug in our values from over here. Okay. F of x plus h minus f of x over x plus h minus x. Now, where did I get these? I have my first point, which is that blue point, the one that I want. And then I have this red point, which is really close to it, but it's just like plus h more. This one is like the y value that goes with it. Okay. All right, I see a question in the chat. So a line for at 1 point is a tangent line and a line for 2 points is a secant line. Yes, that is correct. Okay. All right, so are we okay so far? We've got the slope between these 2 points, one that we know and one that is super close. Okay. So we've been talking about slope all day today, but up until today, we were talking about limits, right? We were talking about limits. And I said that limits was sort of foundational, like concept-wise, because we were going to be using it throughout the session. Okay, so here is the first time that we're going to use limits sort of outside of just limits. All right. Matt asks the exact question that I hope we would ask. This is all fine and good. We know we can sort of find a point close, but how do we actually find that point? And it turns out we can find the point using limits. Okay. So all we're going to do is take this, and if I look back at the graph, all right, in particular, this graph over here, if I want the 2 points to be really close to each other, what does H get really close to? Ah, okay. Let me ask that question one more time. I think maybe my question asking wasn't quite clear. I want these 2 points to be really close to each other. Okay. So what does H, what happens to H? Because if H gets close to X, then I would have like 2X here. H is really small, right? If we want the 2 points to be super close together, then H has to be really, really small. Okay. For the 2 points to be really close together, H must approach, and let's think back to the values that we used before. I think it was, Matt, you said like 0.1 close or like 0.0001 close. And I gave like a really big number. I said like a really small number. I said like this kind of close. Okay. This number is our H value. So H must approach 0. Okay. H must approach 0. And the whole idea of H approaching 0 is exactly what we're going to use to say, turns out we don't even need to know what that second point is because we can just use limits to help us find the fact that they're really close together. So here's what we're going to say, that our instantaneous rate of change, which equals the slope of the tangent line, is going to equal limit as X or as H approaches 0 of that slope. So we're finding the slope between 2 points. However, this H approaches 0 tells us that the 2 points we chose are very close together. Okay. I'm going to zoom in a little bit for this instantaneous rate of change. And let's just see if there are any questions so far. Okay, see if there are any questions so far. Can we simplify the denominator? Does h approach 0 from both sides? These are excellent questions. I'll give folks a little bit more time in case they have more questions, and then we'll kind of answer these, okay? Okay, I love these questions. Let's kind of take them one by one. So one question is, can we simplify the denominator? All right. Let's see. What does that denominator become? Yeah, right, because we have this x minus that x. So then we have f of x plus h minus f of x all over h, okay? So yes, Sophia, we can simplify that denominator. And in fact, this is the more common form that we see. If you look up formal definition or you look up instantaneous rate of change, you're going to get to this formula, okay? Matt, great question. Does h approach 0 from both sides? Yes, it does, because we're not looking, there's no plus or minus sign here. We're just saying that it's going to be 0 from both sides, okay? So IROC is when you already have the AROC but want to find another point. No, that is not accurate. Oh, you rephrased your question. Okay, to rephrase your question, AROC is for when you have 2 points and IROC is only when you have 1 point. Absolutely. Yes, I agree with that rephrasing. Okay, and then one last question here. If you sub in 0 for h, doesn't everything come out to equal 0? I love that you're thinking ahead, right? Because we have a 0 that's going to be on the bottom. That's a problem for us, right? Good thing we learned so many ways to simplify or take care of that fact when the denominator is 0. We're going to use some of those in just a little bit, okay? All right. So make sure you take some time to marinate on this slide or this page in particular, okay? I think that this concept here of average rate of change versus instantaneous rate of change is so very important, okay? It is, in fact, I would say very fundamental to the next few weeks. And I would be so sad if you left this class without a strong understanding of that average rate of change versus instantaneous rate of change. Okay, I see one more question here. So we could choose an h point at the left of our point, and so our h would be x minus h instead of x plus h. Yes, so that's not technically wrong, right? Or correct? Because you're right, we could have picked a point that was on the left, okay? But how many of us in here prefer to work with positive numbers? Anybody here prefer to work with positive numbers over negative numbers? Yeah, right. When we see positive numbers, it just makes it a little easier because we don't have as much to worry about, right? We don't have as many sign mistakes to worry about, et cetera, et cetera. And so in creating this definition here, I think folks decided, let's just assume that h is going to be like a plus h. Because at the end of the day, that value is so small that it's not really going to matter whether we approach from the left or the right, because all of this is only true if it's continuous. And so if we're going to end up with the same answers anyway, why not just make our life easier and just call it a plus? Is really sort of the thinking behind that. Okay, so that is a great question. And I would say, yes, if it was to the left, it would be x minus h, but sort of conventionally, we try and make this much easier for ourselves so that we just keep it a plus h, okay? All right. Well, folks, I think this is a great time to take our break number 2. Okay, so let's take a break until, let's see, 8:48. Okay, take a break until 8:48. We're going to come back and we are going to finish with 3.2. Absolutely. Whoops. Is this good? All right. So I'll see you folks back here in about 10 minutes. Okay.